I don't know how to start this video, so I'm just going to start with the problem. We're looking at LeetCode 202, happy number. This is an easy problem, and the brute force solution requires the brute force solution requires very little data structures and algorithms knowledge. The slightly better but still suboptimal solution requires knowledge of one data structure, and the optimal solution requires knowledge of a data structure and algorithm. So I think this problem provides a great progression when finding the optimal solution. So I'll be going over 3 solutions, but first we'll do it by hand. The problem states, write an algorithm to determine if a number n is happy. A happy number is the number defined by the following process. Starting with any positive integer, replace the number by the sum of the square of its digits. Repeat the process until the number equals 1, where it will stay, or it loops endlessly in a cycle, which does not include 1. Those numbers for which this process ends in 1 are happy. Return true if n is a happy number and false if not. And they give us an example using the number 19 and the number 2, where 19 is happy and 2 is not. We'll go through this by hand really quick. So 19 is our happy number, but we'll just go through it really quick. So this is equal to the sum of its digits squared. So this is equal to 1 squared plus 9 squared, which is 82. 82 goes to 8 squared plus 2 squared, which is 64 plus 4, 68. Took a little bit. 68 equals 6 squared plus 8 squared, which is 100. And 100, might be able to see this one a little ahead, goes to 1. Now 1, just for, writing explicitly, goes to 1, meaning that this is a cycle. And we can continue this process forever, but it will always just go to 1. And so this is a cycle at the end. And what's one thing worth noting is that if instead of 19 we started with 82, we would still go to 1. If we started with 68, we would still go to 1. 100, we'd still go to 1. Any number which is happy along its way identifies other happy numbers. But let's start with one that is not happy, just to demonstrate what this looks like. 2, this one is going to take a little longer. 2 goes to 4, 4 goes to 16, 16 goes to 37, 37 goes to 9 plus 49, 58. 58 goes to 25 plus 64, which is 89. 89 goes to 64 plus 91, which is 155. 155. Did I do all that right? No, this is 81. Oops. This is 145. 145 goes to 16 plus 25. 17, 32, 42. 42 goes to 20, and 20 goes to 4. And so here we have a cycle. We've gone back to a number which we've already been at. Whereas 1 is a cycle of length 1, this is a cycle of 1, 2, 3, 4, 5, 6, 7, 8 distinct numbers. And because we never encounter 1, this number is not happy. And so we would return false, where this returns true. This problem requires that all numbers eventually reach a cycle. I won't go into exactly why or how, but all numbers do eventually reach a cycle. And we can just use that as an invariant. So now we've done it by hand. We're going to first walk through the brute force solution, which requires only the knowledge of an array, some kind of iterating loop, like a for loop or a while loop, and some basic math. After that, we'll get to using a data structure, like a hash set. Then we'll get into the optimal solution, which uses an algorithm for cycle detection, along with the hash set. So for the brute force, we first, of course, need to be able to determine the sum of a number's digits squared, or the sum of a number's squared digits. We can just call this f. So f of n outputs the sum of the squared digits of n. There are several ways to do this. The simplest to code, but slightly less efficient, is to just treat n as a string. And so I'll be writing this in pseudocode, which is quite adjacent to Python. If we have n, which is an integer, we can just convert it to a string and then iterate through its digits, which are now characters. So for c in n as a string, we can have a sum that we're going to be adding to, and we can just say sum plus equals the integer of c squared. And then we'll just return sum. The only reason why this is slightly less efficient is because we're taking up a little more memory, in that we have to now store n as a string. And we also take up a little more computation by turning n into a string and then recasting it to an integer. This does not actually impact the asymptotic runtime, though. The time complexity of this is on the order of O of d, where d is the amount of digits. Because this for loop runs d times, meaning that if the number was a 2-digit number, it runs for 2 iterations. If it's a 10-digit number, it runs for 10 iterations. And the time it takes to construct the string n is also of order nd, or of O of d. And this, which, just to be explicit, is on the order of log n. More specifically, it is log base 10 of n. Because this digit is base 10, the number has to increase by an order of 10, meaning that if we had the number 23, this would take 2 iterations of this. It would make this for loop run twice. In order to make it run 3 times, we would have to go up to like 100. This is 5 times larger. If we wanted to make it go up to, so this, let me just be a little explicit here. This runs 2 times. This runs 3 times. In order to run 4 times, we'd have to go above 1,000, which runs 4 times. This increases by 10. Every time it increases by roughly 10. It could go from 2 to maybe 20, but it'll be on the order of 10. That's because we're in base 10. So to add another digit, we have to go up around a factor of 10. So this is, I don't know if that was obvious, log base 10. Log base 10, just to be, in case you don't know, is the amount of times we'd have to divide a number by 10. So 1,000 log 10 is 1,000 divided by 10, 100 divided by 10, 10 divided by 10, 1. Is log base 10 is 3. So this runs on the asymptotically log base 10 of n. The space complexity is also O of d, which is log n. The slightly better way of doing it is to not have to cast it to a string and instead do everything mathematically. The time complexity of this is exactly the same because we can't get any better than O of d. We have to at least look at every digit in order to sum the squares of the digits. And we can't get any better in the space complexity because the output we're getting, the sum, also grows with the amount of digits. And so the asymptotic runtime won't be any better, but it might be a little cleaner and it also might be good to learn. The better way to do it, well, so asymptotically it's not any better, but realistically it's about 2 times faster. Well, not 2 times faster, but you do reduce overhead, but it is 2 times more memory efficient. Now let's look at why. If we have our sum, and then we'll do it, this way is a little more of a human way of doing things. For example, if we had the number 234, the past way was reading left to right. This way we'll read right to left. What we'll do is we will first mod this number by 10, which will be 4, because 230 is divisible by 10. And then to sort of get rid of this number, we'll divide it by 10. And cast it to an integer. which is also the same as doing integer division. So we might not have to do this cast depending on the language. I think JavaScript will just cast this into a float for you. But something that's more strongly typed, like Java, C++, or even Python, depending on how you set things up, not to say that Python is strongly typed, will just do this as integer division. But the way we know to stop is when n is exhausted, meaning that n is zero. So while n is greater than 0, sum will plus equal n mod 10 squared, and then n is equal to n divided by 10. This is integer division, in case you don't know. As I said before, this time complexity is the same. It's O of d. We're never going to be able to do less iterations than that. And the space complexity is still O of d, because sum grows at the same rate. But we reduced the time overhead of creating a string, and we've reduced the space complexity of having the string. So we kind of have divided these by 2. Asymptotically, this is the same. But if you're really doing this and you had huge numbers, this would matter. Be about 50% faster and more memory efficient. Now, let's get back to the actual problem, which is, so assuming we have f of n, how do we determine if a number is happy or not? The brute force solution is to try and remember everywhere you've been using an array. So we'll call this visited. And while n does not equal 1, we will say that n is now, well, so let's put n in visited, and we'll just assume we've already been there. While n is equal to f of n, so we've summed the squares of its digits, and then we say if, well, we'd say for v in visited, if n equals v, then that means we have seen this before without getting to 1, and so we will return false because we're not a happy number. We had a cycle which wasn't 1. Otherwise, visited plus equals our new n, which is f of n. And if we ever do exit this, I'm going off the page here. If we ever do exit this while loop, that means that n is 1, which means we're happy. So we will return true. This time complexity is a little complicated. It is reliant on the length of the path. because this while loop goes as long as the path is. In the instance of 19, the path went from 19 to 82 to 68 to 100 and to 1. So the path was 4 or 5 steps long. 2, it was about 8 steps long. And so we can kind of say it's O of P, where P is the path length squared. Because for every step in the path, we have to go and scan through visited, which will grow with our path length. And our space complexity is also O of P, because as this path gets longer, visited gets longer. It's interesting that this time and space complexity doesn't actually grow with n, as we saw that with this algorithm, when n is 2, our time complexity and our space complexity, or not complexity, the computational time and the computational space was higher than with 19. So this is a little complicated. In an interview, it would probably be fine to say n squared and n, but may be good to explain that it's actually more of a function of the path length. Now, can we do better? Most often in life, the answer is yes. The obvious thing here is this part. For v in visited, every step we're doing a full scan of our array. The reason I showed this is for people who may not have as much data structures or algorithms experience. But whenever you see this, and order doesn't matter, the answer is to use a hash set. So let's take a look. A hash set allows you to add and check for membership within the set in constant time. So if instead of saying that visited is equal to an array, we just say it's equal to a new set, which is sometimes denoted in math as this. But in most languages, you'll just write new space set. And then the algorithm is mostly the same. While n does not equal 1, we will we should first add ourselves to the set. We should say visited dot add n, and then while n does not equal 1, say that we'll take a step in our path. So n equals f of n, meaning that we are now equal to the sum of the squares of our digits. And then we'll check for membership. So if n is invisited, then we've been here before and we are not happy. So we return false. Otherwise, we'll return true. Now our time complexity here is now O of P. This is O of 1. It's constant. And we're doing that P times, where P is the path length. Our space complexity is still O of P. because our set just grows linearly with the path length. Again, in an interview, it's fine to say O of n. But can we do any better than this? The answer, surprisingly, is yes. We can get rid of this space complexity. We cannot do better than O of p time complexity. The reason being that you will always have to look at every step, assuming that you don't have any time to pre-compute everything, which in an interview, of course you wouldn't. We have to at least traverse the path. And so this time complexity cannot get better. We can't look halfway down the path and know. But the space complexity can be better. We don't necessarily have to remember every number we took to get there. We only need to know that we reached a path. So let's take a look at that. This will be using something called the tortoise and hare algorithm, or I believe it's also called, I can't really remember, it's something called like Floyd cycle detection or something. I'll have to look it up. Yep, Floyd's cycle finding algorithm. Oops. The way this works is by having two pointers. One which moves twice as fast as the other. The intuition here is that on our previous path, we had 2, which led to 4, which led to 16, 37, 58, 25, 64, 89, 64, 81, 145 led to 16, 17, 25. Was that 42? Yeah. Which led to 20, which led back to 4. In this cycle, if we have something that's moving 2 steps every time something else moves 1 step, we call this a tortoise and hare. So if we begin with taking our hare, which I'll denote with H, taking 2 steps, so going 4 to 16 and then to 37, then our hare would be here and our tortoise would start here. Well, this is after 1 step. I'm sorry. So let me show. The tortoise starts here and the hare starts here. The hare moves twice to here, and then the tortoise moves once to here. Boy, I don't know how to erase things. I think it's obvious. so terrible. 2 more steps, and then the hare is at 89, and the tortoise will only move to 37. The hare again will move twice to 42. The tortoise will move to 58. We'll move twice again to 4. And you can see that the hare will inevitably catch the tortoise. There's no worry of the hare hopping over the tortoise, because at every step, the hare will always check, have I reached the tortoise? They will always find each other if they're in a cycle. And if the number is happy, the hare will come to 1 and end the program. So let's look at how to actually code this. We will have, instead of just having n, we'll have our hare pointer, which begins at n, and our tortoise, which also begins at n. Now, well, actually, let's just start them off by taking their steps. So the hare will move twice, so it'll be equal to f of n, and the tortoise will be equal to f of n. So now, while the hare does not equal the tortoise, if the hare is ever at 1, we will return true. And then we'll just take our steps. So the hare will be equal to f of n because we're taking a step. And we can check. And then we haven't, so we'll take another step. And the tortoise will take another step. And this while loop will keep going. If we ever are equal, then we will also return false. So I ran out of space, but at the end of this while loop, we will return false, because if we ever exited, it meant that our hare and tortoise met each other and it wasn't equal to 1. Now this time complexity is still O of p. It grows linearly with the path length, and our space complexity is now O of 1. Because we only make extra space for the hare and tortoise, and they're just integers. They're just pointers.